Framework equations for calculation of the vacuum quantum properties. Using dimensional analysis containing the 5 universal fundamental constants together with a Planck mass density term taken to a simple power, it is possible to express the Planck quantum thermodynamic electrostatic properties as. The quantum properties calculated here are mass, volume, entropy, charge, temperature, pressure and entropy density. Hypothesis. The above set of framework equations for quantum properties expressed in terms of the Planck space fluid density limit also will apply in the vacuum space fluid density limit. Using the space fluid constant, psi, together with the framework set of equations, the ratio of a Planck fluid quantum property, YPL, over the corresponding vacuum fluid quantum property, IVAC, can be expressed as. The property-dependent powers are given in tables 1 and 2 below together with the calculated values for vacuum quantum properties. The combined fluid thermodynamics and dimensional analysis approach used to obtain these estimates for the vacuum properties has the potential of providing highly accurate values. Table 1, Thermodynamic properties for the Planck quantum and the vacuum quantum. Additional vacuum properties from dimensional analysis are given in Table 2. Table 2, Electromagnetic and mechanical properties for space fluids. Note that the vacuum has a non-zero viscosity, the Planck quantum angular momentum equals the Planck constant, and the vacuum has non-zero magnetic and electric fields. Application of the first law to a quantum of vacuum space fluid. The first law of thermodynamics for the internal energy of the system, U, as it applies to a single vacuum space fluid quantum, vac equals 1, is given by. Additional thermodynamic relations that follow from the first law are given by. Expansion of dark energy. Expansion of the vacuum at constant energy density and temperature is easily explained as the addition of new vacuum quantum volumes to the system of interest. Expansion by the addition of new vacuum quanta also means that the expansion of space increases the entropy of the system. The expansion of space by the irreversible creation of new vacuum quanta imparts an arrow of time on the vacuum fluid. The thermodynamic properties of space fluid quanta are characterized by 10 key features given below. Feature 1, an equation of state given by the ideal gas equation. Feature 2, an equation of state parameter of unity, vac equals 1. Feature 3, the vacuum space fluid quantum can be described using a cubic shape so that close packing of these quanta completely fills 3D space. Feature 4, equality of minimum classical gravitational and electromagnetic forces on the square faces of a cubic vacuum quantum is given by. Where the permittivity of free space, epsilon 0, is related to Coulomb's constant, Co, as given by epsilon 0 equals 1/4K. Note that this constraint on space fluids suggests that gravitons together with quanta that have electrical charge are the constituents of space fluid quanta. Feature 5, the permittivity of space, 0, is the same for both space fluids. Because the ratio of the quantum charge to its mass is the same in both space fluids. Feature 6, a dimensionless entropy of unity is given by. From this last relation we see that the ratio of the Planck temperature to the vacuum temperature is equal to the corresponding quantum mass ratio, which equals the square root of the space fluid constant, psi. Feature 7, all thermodynamic properties that represent second derivatives or cross derivatives of the quantum energy will be 0 as given by. Where W and X denote the system state variables, e.g., T, P, V, S, which are proportional to first derivatives of the system energy. This constraint rules out interpretation of the space fluids as critical point fluids. Feature 8, there are 0 degrees of freedom in the pressure energy density temperature phase space of space fluids. This means that the phase diagram of a space fluid is a point in temperature energy density pressure phase space. Feature 9, the thermodynamic properties of the space fluids represent maximum and minimum values for fluids. Maximums for mass, temperature, energy density, pressure and charge density for the Planck fluid quantum. Minimums for quanta in nature are the Planck quantum volume and the vacuum fluid temperature, energy density, pressure, and charge density. Feature 10 quantum self-interaction energies in space fluids represent maximum and minimum values for fluids. Quantum self-interaction energies are maximized in the Planck fluid. Quantum self-interaction energies are minimized in the vacuum fluid.